2007 July Lectures in Physics. My name is David Jamieson. I'm the organiser and sometimes presenter of lectures in the program. Our July Lectures in Physics have now been running every year since 1968, one of the longest running lecture series in the University of Melbourne. Our lectures are devoted to addressing fundamental questions in physics, and our theme for this year has been physics breakthroughs. And our lecture tonight is going to be on dark matter and cosmic collisions, and will be given by Andrew Melatos. But before I introduce Andrew, I'd like to ask you all please to switch off your mobile phones. Tonight's speaker is a member of the Astrophysics Research Group here in the School of Physics. Andrew has a PhD from the University of Sydney, where he was also a university medalist. His current research expertise is in theoretical astrophysics, and in particular neutron stars, gravitational waves, pulsars, plasma physics, and superfluids. So Andrew's the sort of guy that regards Euclidean geometry as just a vague approximation to the real world, where the geometry of space-time is strongly warped by the gravitational fields of heavy objects. But he is now deeply involved with the global quest to detect gravitational waves, the most elusive of the waves in the spectrum. And he has got recent publications in the literature on the magnetic fields of accreting neutron stars and turbulence in pulsars. He's also deeply involved with contributing expertise to the development of the physics, the VCE physics program in the secondary curriculum here in the state of Victoria, and has been on many committees in that capacity. Now, before we begin, if the people who are standing up, and we've run out of seating, I'm afraid, if you'd like to sit down, we're piping the lecture into the neighbouring theatre. If you go through the door up there, you can find yourself in a luxurious theatre where you can spread out and relax and eat your popcorn or whatever else in great comfort. So please don't put up with standing. It's just a few metres through the door, and make yourself at home in there. But let us begin. Ladies and gentlemen, Dr. Andrew Melatos. Ladies and gentlemen, now I did forget to advertise this lecture by Professor Joe Silk, one of the most distinguished researchers in the field of early universe studies, who'll be coming here on the 15th of August. So you could regard this as like a 5th July lecture. 6:30 p.m. though, in the theatre next door on the 15th of August. You'd be very welcome if Andrew gives you a taste for astrophysics. Sorry, Andrew.
Okay, well, thank you very much, David, and I'm so glad that you could all come. It's lovely to be here to be able to tell you about some of the things that we find very exciting. The topic of today's lecture, as you know, is dark matter in cosmic collision. And somewhat ironically, given the topic, my talk is going to be largely about this picture, which purports to be a picture of dark matter. Now, we're going to understand this picture thoroughly during the talk, and I'm going to come back to it again and again. Let me just say now that what you're seeing here is a composite image of something called the bullet cluster. Bullet cluster is a galaxy cluster. I'll tell you what that is shortly. And what you're seeing here is direct, photographic in some sense, evidence for the existence of dark matter. This was one of the preeminent discoveries in astrophysics in the year 2006. Okay, so the outline of the talk. First of all, what is this dark matter and why do we believe that it exists? I will begin by explaining to you giving you two examples of indirect historical evidence for the existence of dark matter. The so-called dark matter is characterized by being dark. It is stable. It's long-lived. It was born. It was created very early in the lifetime of the universe and persists all the way through today. And it interacts with other matter purely gravitationally. Not electromagnetically, it is uncharged, not by the weak force that takes place within the nuclei of atoms, but just through gravitation. And it's therefore very mysterious. We don't know what it is. Then I'm going to go through that picture of the bullet cluster. Now there's a couple of things that we need to understand to fully appreciate that picture. We need to understand something called gravitational lensing, and we need to understand something called X-ray emission from shocks. I'll tell you about both of those things so that you can understand clearly why people got excited about that picture and why it is regarded as direct, in some sense, evidence for the existence of dark matter. And then in the last third of the talk, I'm going to speculate, or more correctly, I'm going to pass on some speculations by others on the nature of this dark matter. What is it? Is it a new kind of particle? What can it tell us about particle physics, etc.? Okay, so let's begin by looking at the historical evidence, the indirect historical evidence for dark matter. The first piece of evidence comes from the rotation of galaxies. Now we can look at distant galaxies, both in optical and visible light through optical telescopes and in radio waves. And we can use our telescopes to determine how fast the stars in that galaxy orbit around the centre. Now it takes about 100 million years for a star to go once around the centre of the galaxy, so standing there waiting for it to do that is not an efficient way to do this experiment. But we do have a nice piece of physics that helps us, and that is the Doppler shift. Many of you will be familiar with this. The Doppler shift is the effect that makes the tone, the pitch of a siren increase or decrease as the siren advances towards or recedes away from the observer. Okay. For sound, you hear the pitch increasing or decreasing. For light, what you see is a change in the colour of the light. If the star is moving away, the light is a bit redder than you would expect. If the star is moving towards you, it is a little bit bluer than you would expect. And people have done this experiment of just looking at stars at different distances from the centre of the galaxy and measuring the colour to their light, and therefore inferring the velocity with the speed with which those stars are orbiting the centre of the galaxy. They've done that with visible light from stars, and they've also done it with 21 centimetre radio waves from clouds of hydrogen that sit inside these galaxies. Okay, now having obtained that speed, we then appeal to Kepler's law of planetary or orbital motion. And that law says, this is the only equation in the talk, that the square of the speed of a body in orbit is proportional to the mass enclosed within that orbit divided by the radius of the orbit. What do I mean by that? Well, if, let's say, I go out twice as far as I used to be, so 4 times as far as I used to be, my speed will halve. Now you might think, naively, looking at that if I go out far enough to the very outskirts of the galaxy, so that all of the mass in the galaxy is enclosed within the circle that I draw, then from this relation, the mass enclosed is going to be the same. And so if I keep going further and further and further out, there's no more mass being enclosed because I've enclosed everything. But the radius keeps increasing. And so the speed should fall away. And so I expect, naively, that beyond a certain radius where all of the mass is enclosed, as I keep going further and further out, the speed of the stars should decrease, according to that formula. Because the top is constant, but the radius on the bottom is going to be big. Well, that expectation is indeed naive. The blue line shows that naive prediction. What we're seeing here is a graph of the speed of the stars in kilometres per second, which is fast. And on this axis, the distance from the centre of the galaxy in thousands of light years, effectively. It's a slightly different unit, but don't worry about it. So this is about 10,000 light years. And you can see that the prediction is that the speed of the stars falls away for the reasons that I just said. In practice, in truth, that doesn't happen. Instead, the speed of the stars flattens out as you move further and further out. And that very surprising effect, the so-called flat rotation curve, was discovered by, among other people, Vera Rubin at the Carnegie Institute and from Washington. Now, if we look at our equation here, the speed is roughly constant beyond a certain radius. The radius is increasing as we go out. That must mean that the mass enclosed is also increasing as we go out, so that the ratio of these two things remains the same. Okay? And that is evidence for dark matter, because of course, when you look at a galaxy, you go beyond a certain distance from the centre, there are no more stars, there's no nothing, there is no luminous matter beyond a certain distance from the centre of the galaxy. And yet, our study of the rotation has just told us that the mass enclosed keeps increasing the further out you go. And since you're not seeing that additional mass, we refer to it as dark. Just to give you a very quick, this is exactly the same diagram you just saw, but for a whole bunch of different galaxies in the universe that have been studied. And you can see that for all of them, there are some wiggles, but basically when you go out far enough, the velocity, the speed of rotation remains constant. Okay, so that's the first piece of indirect evidence for the existence of dark matter. And I should say there are heaps and heaps of pieces of indirect evidence, all relatively strong. I can only cover two in this talk. The first we've just looked at. The second is something called the cosmic microwave background, cosmic microwave Higgs, and this is something that many of you will have heard of and read about in various publications. The cosmic microwave background is noise, microwave noise, covering the entire sky. If you go out to your backyard and construct carefully an antenna that measures microwaves, and then you just point the antenna up at the sky, you will sense microwaves coming from the whole sky. The effective temperature that corresponds to those microwaves is about 2.7 Kelvin. So they're very cold. At least currently, they're very cold and reasonably close to zero. And this map is a projection of the whole sky. And what it shows in bright patches are relatively hot patches of this microwave sky, and in blue, relatively cold patches of the sky. Now you might ask, where do these microwaves come from? They come from the Big Bang. They are in fact the relic, the radiative relic of the Big Bang. As you know, the Big Bang, the universe started in a very hot phase. It was an explosion. During that explosion, there was a lot of radiation, and as the universe expanded, that radiation effectively decreases in temperature until you get this pattern that we see today. Now, on the map, I told you that the yellow and red bits are relatively hot, and the blue bits are relatively cold. How hot, or how much hotter, and how much colder? Only a tiny amount. The mean temperature across this diagram, across this map, is 2.7 Kelvin. The fluctuations, the hot and the cold, are about 100,000 of that. So there are very, very tiny differences in temperature across this microwave sky. In fact, so tiny that you need to build very, very clever and expensive spacecraft to measure. Now, just briefly, so that you have a context within which to put these fluctuations, this diagram shows you what happens to them as the universe evolves. And the main thing to take away is that these fluctuations in temperature, which also, I should say, correspond to fluctuations in density. These fluctuations are the seeds from which the structure that we see in our universe today, galaxies and all of those things that we know and love, are the seeds from which all of that arose. So you start back here at the birth of the universe with these little fluctuations. And then as time goes by, the universe expands. And as it expands, those fluctuations grow, get bigger and bigger. And eventually, they collapse to form galaxies and clusters of galaxies. That bullet cluster, which we'll be talking about throughout the talk, the evidence for dark matter, is exactly one of these clusters. It came from just a few little fluctuations back here, right at the beginning of the universe, which subsequently grew. And I have a movie which illustrates this. So in the top here, you're going to see a number which starts off big and becomes small. That is the so-called redshift. But just think of it as time, in some sense, before the present. So we start a long time ago, at the beginning of the universe, and we will steadily, as we play the movie, progress through to the present. And what you see here is a mess. In fact, you're seeing the hiss, those little fluctuations in the microwave sky. But as the movie plays, you will see these fluctuations grow and coalesce and form these very beautiful structures. Filaments, voids, arcs, clusters of galaxies, and then galaxies within the clusters of galaxies. And that situation is the present day. Okay, now, this little satellite, WMAP, was launched to measure very, very accurately the distribution of temperature on that map of the microwave hiss that I showed you before. So that satellite measures, basically produces that map. It has two little feed horn antennas, which you can see there and there. And as the satellite tumbles, it looks at those antennas point at different points on the sky, and you construct a map for how the temperature fluctuates from place to place. This graph is the result of that WMAP experiment, which incidentally was another, the WMAP is one of the great experiments in astrophysics. It was done, the results were published about 2 or 3 years ago. And here they are. Now, what you're looking at here, effectively, is a graph of the brightness of the patches on that map versus their angular size. So, don't worry about these technical words, they're not important. Just think if you're high on this axis, you're bright. And if you're further to the right here, you're looking at smaller angular scales. So that's 0.2 degrees, that is 2 degrees. And what you can see is that at certain values of the angular scale, you get particularly strong microwave emission. The height, position of these peaks, and there are several of them that have been measured, tells you about, among other things, the contents of the universe. It tells you about the ratio between total matter, baryonic matter, which is the stuff like this, that we know and love, and radiation. And when you know this ratio, you can subtract this baryonic matter from the total matter. And what you get is the amount of dark matter that must be present. So this is the second piece of evidence for the existence of dark matter, because when you crunch through the theory and do that subtraction, you find that there's plenty of dark matter around. Dark matter is necessary to produce that beautiful curve, and you'll notice that the data is extremely accurate here. That grey shows you the accuracy of the data. There's no question. If you didn't have the dark matter there, the agreement between theory and data would be atrocious. so what are the ingredients of the universe? Well, there's this microwave background. We put that together with some other data which I'm not going to describe to you tonight because it would take us too far afield. High redshift supernovae and galaxy surveys, such as the 2DF survey that was done here in Australia. But the net result, when you put all these things together, is that the universe has three important components. 4% of it is atoms, like the atoms making up this table. 22% is the dark matter that is the subject of this talk. And then 74% is the so-called dark energy. Now, I want to quote an astrophysicist, Daniel Eisenstein, who says that the phrase dark energy overstates our understanding of what dark energy is by a factor of 2. It is dark, but it may not be energy. And the dark energy is associated with the cosmological constant that many of you may have heard of, and the fact that the universe is currently accelerating. Depending on who you speak to, this cosmological constant and the dark energy should either be ridiculously larger than they are measured to be, by 10 to the 120 times larger. There's 1 with 120 zeros after it. Or else it should be 0, rather than the value that it's measured to have. Which is unsatisfactory. And because it's unsatisfactory and a little bit embarrassing and a long story, I'm not going to talk about it here. Okay. So there is the evidence, there's the indirect historical evidence for dark matter, the rotation curves of galaxies, and the cosmic microwave background. The next topic that we're now going to cover is this evidence that I've been telling you is very exciting, namely photographs. I use the term somewhat loosely, of dark matter. And photograph is that of the bullet cluster. Now, let me start by telling you briefly what a cluster is. Galaxy cluster is a structure within the universe that contains up to 1,000, sometimes even more galaxies. That's huge. Imagine our sun is one of 10 billion stars in our galaxy. And what we're saying is there are 1,000 or more of those galaxies inside a galaxy cluster. Galaxy clusters are millions of light years apart. And what you're seeing here is a Hubble Space Telescope picture of the galaxies in such a cluster. These are not stars, these are galaxies, very, very far away. Just to give you a sense of perspective here, I have a little movie which starts by focusing on one galaxy in the center and then zooms out so that you can see the whole cluster. Galaxy, galaxy, more galaxies, more galaxies. They're coming in from everywhere. You end up with that picture. So this is just a huge system, very far away. Okay, now, there are colours in this picture, and it's very important for the talk that you remember what these colours are. So let me introduce them. Firstly, the white and orange dots are the galaxies. We've just talked about those. They came from the Hubble Space Telescope. Secondly, you can see these pink fuzz. Now, the pink fuzz is hot gas, mainly hydrogen, inside the cluster. And because the gas is very hot, it emits X-rays. Those X-rays have been observed by the Chandra Space Telescope, and that is the image that Chandra produced. That image is colour-coded in red. Finally, there's the blue patches. Now, the blue patches are not observed by any telescope directly. They are inferred from a piece of physics called gravitational lensing, which we'll discuss shortly. But where you have the blue in that picture, is where the dark matter is known to be. And I'll tell you why we know it's there in just a moment. Okay. And what's going on in this bullet cluster is that the two clusters merge. They're attracted towards and through each other by their own gravity. And clusters do that, by, in astronomers' terms, relatively often, every billion years. And so they might have 10 or more such mergers during the age of the Okay, now before I tell you about the specific techniques that go into measuring the pink and the blue in that diagram, let me run through from that diagram the argument for the existence of dark matter. And this argument, I think you'll agree, is very robust because it really doesn't rely on very much thought. Now we're going to start by looking at the gas. Remember, the gas is the pink stuff. As the two clusters come together, each with their own galaxies and with their gas, the gas, as they merge, collides and then passes through. I'll show you a movie of this in a moment. But the important point is that because it is gas, it, as it collides, decelerates, not just gravitationally, but also collision through friction. Okay? Because gas is like air, you know, that air or water or any fluid has friction in it. And what that means is that the gas, because it slows down through both of these mechanisms, lags behind the galaxies. And you can see that. Let's just pop back and show it to you where it's larger. This cluster was once upon a time on the left, and this cluster was once upon a time on the right. They've now passed through each other, and you can see that this one's moving that way, this one's moving that way. The red gas lags behind the little white galaxies in this cluster. And this one that's moving that way, the red gas lags behind these white galaxies. Now, the galaxies, on the other hand, decelerate purely gravitationally. They are collisionless. Even though that might seem a little strange to you, that you've got these huge agglomerations of billions of stars, and they run through each other, and none of the stars ever collide. And I agree, that is naively, on the face of it, that is quite strange. But it is true. You can calculate how long it would take for two stars to collide in such a situation, and it's just forever, not forever, but a very, very long time. So, to all intents and purposes, the galaxies and the stars within them are collisionless. They just pass through each other. And so, as they come in, they speed up because the gravity pulls them together. As they pass through, they slow down because the gravity is pulling them back. But there's no collisions of any sort. And because of that, they outrun the gas. And that's why the gas lags behind the galaxy. Now the fourth step of the argument is the dark matter. Using this technique of gravitational lensing, which I'll talk about shortly, we find that the dark matter, the blue patches, are coincident with the galaxies, not the gas. And so since the galaxies are collisionless, the dark matter, which we can't see, must be collisionless as well. It is behaving, this dark matter is not behaving like gas. It's not behaving like baryons, which make up this table. It's a different thing that only interacts gravitationally, not collisionally. Now, it's very hard to get away from that conclusion, and that is why that has been counted, probably correctly, as the first direct proof of the existence of dark matter. Now, let me run through the techniques involved. The first technique pertains to the red gas, the gas that was coloured pink in those diagrams. You will remember that, especially in this one, there's a very beautiful wedge shape enveloping that gas. And that wedge is called a shock. In particular, it's called a bow shock. Now, shocks occur on Earth as well. They occur whenever you have two fluids in supersonic relative motion. And at a shock, the pressure, and a bunch of other things as well, jumps discontinuously. So a classic example of a shock is a sonic boom from a plane. You know that the pressure jumps discontinuously because when the boom hits your ear, it hurts. That's because now, what happens in a shock is that all of the motion in the gas colliding together, the kinetic energy in that motion is turned into heat. And we're talking here about very fast motions, 4,500 kilometers per second. So the temperatures that you get as a result are very high, 1 billion degrees. And that's why you can see those X-rays from so far away. The details of the X-rays tell you the temperature and density of the material, and from that you can deduce the speed with which the gas is colliding and also the direction they're colliding, because that little wedge shape points effectively along the direction of motion. And that diagram here shows a little apparatus that you can use to make shocks in at home, so to speak. It's a little bit more complicated than that. Okay, now just for fun, let me show you some terrestrial examples for shocks. This is the blast wave after a nuclear explosion, caught just after a nuclear bomb has been detonated. That's data, sadly enough. Here are the shocks induced in air past a fast-moving car. You can see there's many of them. These photos are called Schlieren photos, for those who are interested, and they're taken with a very clever technique. So you can see there are about 3 shocks in that picture. And then here is a bullet traveling through air, and you can see the sonic boom around the bullet, and then which is the shock, and then a very pretty turbulent wave. More pictures. Here is a fighter plane just going through the sound barrier, and that cloud is condensation at the shock that is produced. Here is a duck swimming through water, and you can see the bow wave that it puts behind it. Now, you might say, well, surely Andrew's been saying that these things happen when you move supersonically. The speed of sound in water is very fast, way faster than the duck could possibly swim, and that's correct. But you need to remember that it doesn't just need to be greater than, it's not just a question of being higher than the speed of sound. It needs to be higher than the speed of the waves in your medium. And in this case, the water waves on this pond will travel slower, much more slowly than the duck can swim, and that's why you get that time. And then you just get shocks in astrophysics. This one here is the shock, the toroidal shock around the Crab Nebula, which I love because I work on it. There's a pulsar in here, a neutron star, sending out relativistic electrons and positrons, and they smash into your surroundings, and you get that. But that's off topic, so I'm not going to discuss it in person. Here is the Chandra satellite, which took the X-ray photos that I showed you before. And so putting all of that together in this movie, what you see is the blue is the dark matter, the red is the gas, the two clusters move through each other, and you end up with the picture of the cave stuff. Okay, so that's the X-rays and Chandra are how we found out about the gas. The other half of our dark matter proof, existence proof, involves finding out where the dark matter is, and that is done by gravitational lensing. Now, gravitational lensing, again, many of you may have heard of. Einstein said that mass, or equivalently energy, curves space and time. If you are near a massive body, distances are slightly stretched, and time intervals lengthen. Light waves, it turns out, move along paths of least resistance in this curved space-time. So I'm attempting to illustrate that here. Here's an apple sitting in the middle of a piece of curved space-time. Think of it as a rubber sheet. And here's a photon, a light ray. Think of it as a little billiard ball, just for the moment, which rolls along the rubber sheet. And you know, just from common sense, that that billiard ball is going to go into the dimple and then shoot out the other side. But when it shoots out the other side, it will no longer be travelling along the same straight trajectory with which it came into the dimple. In other words, the billiard ball is deflected. And light rays behave in exactly the same way. When they pass near a massive object, they are bent as a result of Einstein's theory of relativity. The angle with which they are bent is proportional to the mass of the object. Obviously, if I take a car and drop it into the middle of that rubber sheet, it's going to make a huge dimple. And then when I send the light ray past, it's going to almost make a 180-degree turn. And so from the bending angle, you can tell the mass enclosed, and that's important because remember, we're looking for dark matter. It's something that we can't see directly. We're looking for independent, indirect manifestations of its existence. Now, you really need more than one light ray and more than one source to measure the mass in these systems. So I've got here a little picture. It's extremely crude, and I apologise for it. But what you're seeing here are 4 galaxies, which are meant to represent that galaxy cluster that we saw before. So this is the cluster. Here is an object, it could be a quasar, just something, a long way behind the galaxy cluster. And here are we observing the light from this distant object. Now what happens is the light comes along, it bends just like this, and strikes the observer. But because our brains are trained to think that light comes in straight lines, we think that this object is actually up here. This image that we see is our brain extrapolating the light ray that we observe on Earth and extrapolating it backwards to say that the image must come over here. Now, you can see immediately that if all I have is one image, I don't know how much mass is enclosed. Because I could have a lot of mass and a light ray which passes relatively far away. Or I could have only a little bit of mass, but a light ray which passes very close. And in both cases, my image is going to be in exactly the same place. Okay. So just from one image, I can't distinguish. I need multiple images or rings. And here are some beautiful Hubble Space Telescope pictures of gravitational lenses with multiple images. And you can see here, 4-image one, which is across, 2 images over here, one with sort of half an arc, 2 images, a nice complicated one with 4 images in a row, etc., etc. And if we're lucky, and the object we're viewing is almost directly behind the cluster that is acting like the lens, then rather than separate images, you get these lovely rings. Now, the story is a little bit more complicated, and because that discovery is important, I will spend one slide talking about this. The pictures I showed you there are for a single object like the galaxy cluster, imaging, lensing, light from a single object behind. But in truth, both the dark and the luminous matter within a galaxy cluster is actually hierarchical. It has a lot of substructure. Okay? What I've said there is bubbles inside bubbles. So, you know, if you imagine your galaxy cluster has a sort of spherical shape, but there are clumps inside it that are denser than other clumps. And then inside those clumps, there are other little clumps that are even denser. And all of those are randomly distributed. And so your lens, rather than being a beautiful lens like the one in your spectacles, is very corrugated and messy. There's bits of mass here and there, and they're in random places. And when you have a corrugated lens, you don't get perfect images. You get arcs and what are called caustics. Now, I'll show you a very pretty picture of a caustic in a second. Caustics are what you get when you look on the bottom of a swimming pool. There's the sun coming down, and the water is not too choppy, but nor is it completely flat. You get corrugations in the surface of the water, and the light refracts, and there are places on the bottom of the swimming pool that are very bright, where lots of light rays converge, and there are other places which are less bright, because no light rays converge there. And you all have seen that sort of thing. That's actually a photo from the bottom of the swimming pool. Now, the amount of corrugation determines the kinds of arcs and pictures that you see. This is a lens which is very smooth. It just has a few blobs of matter, of substructure in it, which are moving around, I should say. And as they move around, you get these caustics, these bright arcs, but they're sort of few and far between. If we now move to a medium level of corrugation, then you get many more bright arcs and much richer structure of caustics. Caustic, by the way, comes from a Greek word, which means burning. That's why it's used for alkalis like soda. And it's relevant here because, of course, as you know, if you put your hand under a magnifying glass, those caustics, those bright patches that we're seeing, if they're produced, say, by sun, are hotter than the ones that surround. And then a high degree of corrugation with lots within your galaxy cluster will produce that sort of behavior. This is gratuitous. It's a kangaroo in front of a galaxy cluster, and the result is the kangaroo is torn to shreds. And this is not gratuitous. This is a real picture of the Abel cluster showing what happens. So you'll see that there are these. This is a real Hubble Space Telescope image. You'll see these long, stretched out arcs. And these arcs are background objects that have been lensed in a complicated way by the rough matter distribution within, dark matter distribution within that cluster. So the point, apart from showing you those pretty pictures, the point of this is that if you understand the theory of gravitational lensing, which is just Einstein's theory applied to that particular problem, there's nothing mathematical, but there's nothing mysterious about it. If you understand how that lensing happens, you can reconstruct an image like this, which also has arcs. They're a bit harder to see here. There are various little arcs, just like the arcs in the previous diagram. You can reconstruct from those arcs exactly where the dark matter sits in your field of view. And people have done that for this picture. So it was a hard job, and it needed to be done very carefully. But when they did it, they found that the dark matter sits there and there. And as I keep saying, that is coincident with the collisionless galaxies, but it is separated from the collisional gas. And so this dark matter is behaving differently to the gas that we know and love. Okay, now one nice thing about, so that's the proof. That's why we know that dark, or the way we believe now the dark matter exists. There were some nice bonuses that came out of that study. The first was to kill off a theory that very few of us actually liked, but which was not actually ruled out until now. That is modified Newtonian dynamics. People said, well, maybe those rotation curves, those galaxy rotation curves I mentioned at the start, have nothing to do with dark matter. Instead, they are caused by Newton's law of gravity, which underlies Kepler's equation, the one that we saw right at the beginning. maybe that law of gravity is wrong. Maybe when you get to large scales of thousands of light years, gravity doesn't behave as a 1 over r squared law, it does something different. Okay? And then you don't need dark matter at all. Well, if that was the case, then you would have expected the lensing, which produces these blue patches, to coincide with the gas, which carries the majority of the mass in the cluster. I mean, nobody was saying that modified Newtonian dynamics divorces itself from mass. It was still, the idea was still that mass produces the gravity, but just with a different law. And so, if it were true, you would expect the blue to be congregated around here, and it just isn't. So that's good. The second thing, and I won't spend much time on this, is just to say that since we know the galaxies are collisionless, and we know that the dark matter lies on top of them, therefore the dark matter light is also collisionless. But if there was some separation, even a little bit, between the galaxies and the blue patches, then that would be telling us that the dark matter is not quite collisionless. It's a little bit collisional, not much, but a little bit, and it interacts with itself. Okay? But there's no evidence for that. Very careful studies of that picture show that the galaxies, the white spots, and the dark matter, the blue patch, lie exactly on top of each other. And so the people who did that study used it to put a limit on the cross-section of the dark matter self-interaction with this value here, and that's quite interesting because it then becomes too small to explain some other things, which I won't go into, that people have been hoping it would explain. Okay. So, that's the end of the observations. Let's entertain briefly some speculations. And I have here a famous quote by Isidore Rabi in 1936, who said that when he learned of the discovery of the muon. You know, up to that point, everybody was quite happy with protons and electrons and neutrons and saw no need for any extra things to spoil the picture. But they were there, and you have to explain them. Likewise, nobody in their right mind would have sort of wished to have the dark matter there, if one could possibly help it. But it is there, and so it's very interesting. We need to explain what it is. And of course, we're hamstrung in that attempted explanation because it's dark, and therefore we can't really study it very carefully. However, we do know some things, and we're going to have to use these to make some progress in our understanding. The first is that dark matter is long-lived. Now, I've already discussed that. It has to be long-lived. It has to be stable for billions of years because it was there at the early universe when the cosmic microwave background was formed. Remember, I told you that map of the CMB, the cosmic microwave background, needed dark matter to be present to get the shape that it does. Okay? And that was way back, very shortly after the Big Bang, billions of years ago. We also know that dark matter is in those galaxies from the rotation curve. And those galaxies are here today. So clearly the dark matter has survived for a long time. That puts limits on the kind of particle it might be, and I'll talk about that. Secondly, the dark matter has to be cold. By cold, I mean it moves relatively slowly. And it has to move slowly for a technical but important reason, which is that if it doesn't move slowly, those beautiful filamentary structures that we saw in that movie, the ones which sort of form throughout the universe, simply can't form. They would get smeared and washed out if you didn't have cold dark matter. And because the dark matter is cold, that must mean that it is composed of heavy particles. It can't be composed of light particles, because if it were light particles, they'd be whizzing around like crazy, and that would then stop the structure, the filaments from forming. And thirdly, the matter has to be non-baryonic. In other words, not like this table, or like hydrogen, or any of those things. And again, there's a technical reason for that, to do with the creation of the first generation of elements after the Big Bang. We know very well how much helium, how much lithium, how much deuterium was created during, or just after the Big Bang, and you need the dark matter to be non-baryonic to get those relative abundances, those relative proportions correct. So, as a result of this, you're led to WIMPs, which are weakly interacting massive particles. And then the question is, how do they fit into what we know about particle physics today? Well, let me summarize very, very briefly what we know about particle physics today. These are the families of fundamental particles. And what we have here are three different kinds of them. On the right-hand side are the particles that carry the forces of nature. So the photon carries the electromagnetic force. And these two guys carry the weak force, which occurs inside nuclei. This one carries the strong force, which also occurs inside nuclei. They're called bosons. Don't worry about what that is. I'm sure, in fact, that this was discussed in detail in the previous July lecture. Over here, we have quarks, 6 different types. And the quarks appear in triplets inside things like protons and neutrons. The constituents, as far as we know, of protons and neutrons, and they feel the strong force. Over here, we have leptons, things like electrons and muons, and these neutrinos. And they are very light particles, hence the name, which feel the weak force, the electromagnetic force, etc., and participate in reactions with all these other particles. Here's an example of such a reaction. This is, don't worry about the details, but what you're looking at here is the Feynman diagram, the famous American physicist Feynman. And just very briefly, we've got an electron and a positron, which is its antiparticle, merging, forming a photon. Time goes to the right here. And that photon then makes a quark and an antiquark, and then a little gluon comes out of one of those quarks. It has no relevance other than to show you that these are the sorts of reactions that can involve all the particles of the sort of form. Now, the particles on this diagram have masses, and those masses need to be created by yet another particle, or field. That field is called the Higgs Boson, and looking for the Higgs Boson, as you may have heard last week, is one of the things that that the experimental particle physics group here at the University of Melbourne is directly involved with through their experiments at CERN. Now this Higgs Boson, is another particle. We don't need to worry about the detail. But it has an interesting property. Like any particle, as it moves along, it's cloaked by this fizzing kind of sea of particle and particle pairs. Things like quarks and antiquarks suddenly pop up out of nowhere, live for a very short time near the Higgs boson, and then disappear. So the Higgs boson is going on. It's like it's got this ball of flies, wad flies around it, just passing away. Except the flies keep appearing and disappearing, and on very, very short. You can't in the wink of an eye. The net effect of all of that, though, is that the mass of that Higgs boson, as it's surrounded by all these buzzing flies, is different to what it would be if the flies were not there. Now, why that is very subtle and complicated, and I'm not going to try and discuss it, describe it here. But the environment of fizzing particles that this Higgs boson sits in changes its mass. And that occurs through a Feynman diagram like this. And the change is as follows. What you get for the mass that you observe, which is called the dressed mass, because it's the mass that you get when you've got the cloak of fizzing particles when you're wearing that cloak. So this is what you actually see. This mass is something called the bare mass, which is what you would have if you didn't have the fizz there, minus the Planck mass squared. And you immediately run into a huge problem, because the Higgs boson is known to be at around a mass of 100 GeV. The Planck mass is billions and billions of times bigger than that. It's huge. And so if you're going to subtract this, so if you're going to subtract this from that to get something very, very small, these two things must be almost the same. And that's a miraculous coincidence. In fact, we would always say it's an incredible coincidence. And so people don't believe it, and they call it the fine-tuning problem. Now, how might you solve the fine-tuning problem? Well, solving the fine-tuning problem also, and this is why I'm talking about it, produces some nice candidates for dark matter. And I'm going to very briefly talk about two solutions to the fine-tuning problem. The first is something called supersymmetry. Particle physicists love exaggeration, so it's always super and bigger and the rest of it. And supersymmetry is just a new kind of symmetry. We don't need to worry about the details, but what it says is that every normal particle, electrons, whatever, has a superpartner, a new particle called a superpartner. And the superpartners are imaginatively named as the old particle with an S at the front. So electron would be selectron. Yes, no, I might have got that wrong. There are some strange ones in that zoo of names, which are quite cute. But anyways, now, why does that solve the fine-tuning problem? Because when you crunch through all the theoretical physics, you find that this term, this huge term that was causing all the trouble, is cancelled out. When you have the superpartners there, you get another thing here, which is plus 10 to the 19 GeV squared. So that term disappears completely. And then there's no more fine-tuning problem. Now, it turns out that the superpartners always interact in pairs. There are symmetry conservation laws that dictate that. And that means that the lightest superpartner, cannot decay. Cannot have a situation where this lightest superpartner suddenly turns into some other stuff. It's not allowed within this theory. And this lightest superpartner is called the neutralino. It has the name chi. It's uncharged, hence the name neutralino. It is weakly interacting. You can send it through kilometres and kilometres of lead and it doesn't bounce off anything, it just keeps going. And it has a mass or an energy of roughly the right number that you need to explain the dark matter. And so this is actually one of the best, in some sense, one of the best dark matter candidates. It is also in just the right range to be looked for by the LHC, the big experiment at CERN, which was probably discussed in the previous two. Okay, so that's one kind of solution to that fine-tuning problem, which gives us a possibility for dark matter, neutralinos. And they're a respectable possibility, which is why I'm discussing them with you today. Okay, the second possibility I want to discuss are extra dimensions. Now, why on earth should extra dimensions produce new particles like dark matter? Well, first we need to understand what extra dimensions are. Our world has 4 dimensions. 3 dimensions of space and 1 dimension of time. And all of those dimensions are infinite. We can go as far as we like in any direction, and we can go, we believe, as far forward in time as we wish. However, theoretical physicists, mathematicians, something, have posited the existence of other dimensions which are curled up in tiny loops. So at every point, right here on the tip of this table, there's also these tiny little extra dimensions, tiny little loops that I can't access because my X-ray glasses are not good enough. They're just stuck in there, and they're absolutely minuscule. Now, we've got a very nice two-dimensional analogy for that, which is this Perspex tube. Imagine this tube was infinite. We've got one dimension that can go as far as you like, but then we've got another dimension around here which is compacted light. It's curved. Okay. Now, I still haven't said why this makes dark matter, but I'm about to. You probably know from quantum mechanics that particles are waves. It's a whole separate topic in itself, which I'm not going to discuss. We'll just take that as given that every particle is actually also a wave. And so what I've got here is, I spent a lot of time preparing this demonstration, but what I have here is a high quality rendition of a particle, which is also a wave. Now, this wave needs to exist in the space in which it sits. Okay? And at least the way I've drawn it here, it could go on forever, and that's fine because we've got forever to go to the left and forever to the right. But when we're talking about our curled dimension, that's no longer true. You can't go forever around the curled dimension without sort of catching your tail. And so we have to make sure that our particle, our wave, fits perfectly around our curled dimension. I'm not sure if people can see that. Okay. And it has to fit, when I say fit perfectly, it has to fit so that there's a perfect match. The wave here just continuously carries on to the wave on the other side. So that as I go around, there's no discontinuous break in that wave. Okay. Now if you think about it, that tells you something about the wavelength of this wave, the distance between peaks and troughs. It tells you that the wavelength can't be too long. Because if the wavelength is too long, like this, then when I try and wrap it around the tube, no matter how hard I try, there's always going to be a spot where it doesn't fit together neatly. Okay? Where the wave makes a sudden break. And nature doesn't like those kinds of sudden breaks. It disallows them. Okay? And so those long wavelengths, like this one I've drawn here, long distances between peaks and troughs, cannot be accommodated in this extra dimension, in the curled dimension. Now, some of you may know that a maximum wavelength, so a wavelength beyond which you cannot go, corresponds to a minimum energy for that particle, for that wavelength. Okay? If you can't go beyond a certain wavelength, then quantum mechanics tells you the particle, the wave, cannot have less than a certain energy. Now we know from Einstein that energy is just mass. And so this minimum energy is perceived as a mass. It's perceived as mass in our four-dimensional real world. Okay? So the mass, the idea of this, the point behind this theory is that the masses that you get, and therefore the dark matter, possibly, is just the minimum energy that comes from the waves not being able to, or having to fit inside this curled dimension. It's completely different to supersymmetry, completely different possibility, and again, the same one, which is why I discussed it. Now, I'm going to stop in just 5 minutes. Let me finish by telling you about the Wink miracle. So we've been talking about these weakly interacting massive particles. And one thing we can do, irrespective of whether they come from supersymmetry or extra dimensions, one thing we can do is look at how they were created in the early universe. Now, way back, shortly after the Big Bang, the universe was very hot. It was in something called thermal equilibrium. Everything was bouncing off everything else, and everything was at a constant temperature in some sense. And during that thermal equilibrium, there were reactions. And those reactions have, let's say, neutralino plus neutralino back and forth, making fermions and antifermions, different kinds of particles. And these reactions, because it's equilibrium, occur equally quickly in the forward and reverse direction. So two neutralinos come together to make the F and the anti-F, but then shortly afterwards, an F and an anti-F
And it stops because you're going from light particles to heavy particles. So unless you have enough energy, you can't make that reaction happen. And you need to put in energy to the light particles to get the heavy particles. Subsequently, so that reaction stops. The forward reaction keeps going. So the neutralinos just keep getting used up. They collide and they make these guys, but there's no way for these guys to pop back. And so the number of neutralinos just keeps, the amount of dark matter keeps falling away. However, after some more time lapses, the universe expands enough that these neutralinos are too far apart to actually hit each other. And when that happens, the forward reaction stops as well. And at that point, you freeze out a certain quantity of neutralinos. They are the ones that survive, and then they're stuck there. They will not react forwards, and they will never be replenished in reverse. Now, if you want to explain the 23% dark matter, which I told you has been measured before, we said we put together all the data and found that there's dark energy, which is awful and not discussed tonight, and there's the 23% dark matter. If you want to explain exactly the right amount of dark matter, the mass of the neutralino, which controls the rate of this reaction, should be between 60 and 1,000 GeV. And that's extremely interesting because this is a range that CERN, the Large Hadron Collider at CERN, which you heard about last week, and will operate. And so we hope at CERN to be able to see these neutralinos. And if we're lucky, there'll be more than one type of dark matter particle. And if so, that would be great because the different ones would freeze out at different times in different proportions with different abundances. And so you can test the theory that goes behind this work. An extension of that, and this is relatively new and something which was being discussed at the General Relativity Conference I went to about a couple of weeks ago, is something called superwaves. So the hypothesis here is that rather than having a neutralino as the dark matter particle, let's make the gravitino the dark matter particle. The gravitino is the superpartner of the graviton. Now, it starts to get a bit confusing with all these names, but anyway, it doesn't matter. The important thing about the gravitino is that, like the graviton, it is the force carrier for gravity. It only interacts with things gravitational, nothing else. No electromagnetism, no strong force, no weak force, just gravity. It's a purely gravitational object in some sense. Now, if you do this, if you make this assumption, then the WIMPs freeze out at 23%, exactly the same as before. But they immediately decay into the lightest superparticle, which is the gravitino. And so you cleverly have this arrangement where the gravitino, which is the dark matter candidate, inherits the correct density of 23%, but it is a particle that only interacts gravitationally. And remember, that is exactly what we want for dark matter. Dark matter is something that we cannot see, does not feel things except through its gravity. And if this theory is correct, there are nice tests you can do. And my colleague Elizabeth Barbarian was telling me that one of the tests you can do is called drill a hole in the wall. So at CERN, apparently you try and guess where the gravitinos are coming, and then you just take a big core and just cut out some of the concrete in the wall, and then wait for decays of gravitinos, these WIMPs from that piece of concrete. And I only asked her about this just before the lecture, so she may have been having me on, but and there are other tests you can do. And this is the machine that's going to test all of this, the Atlas experiment at the Large Hadron Collider at CERN. Energies of 14 TeV, so ample to look for some of these dark matter particles. 10 million top quarks per annum, compared to the 10 or whatever it is that have been produced so far. It's a bit more than that, but still, and a magnificent piece of engineering which will come online in a couple of years and will have lots of fantastic surprises for us. Thanks very much.
ask a few questions. The gentleman in the dark shirt, jumper, yes, please. First one.
Yes, earlier in the lecture you mentioned, to present the scenario, you had a cluster of galaxies, another cluster of galaxies, they happen to be coming toward each other. Now, with the cluster of galaxies, you also mentioned that they are enveloped in dark matter as well, and the dark matter is go along with the cluster of galaxies. You've also mentioned that before they actually interact, there's no gas yet, no high energy gas, which they're far apart from each other to begin. That, the question I've got, at what rate, when you sort of get a picture of how the gas actually develops, as they actually come through, you're not mentioning hydrogen gas, and that goes to high temperatures, what would the temperature be throughout that region? What is the size of that region? And would the heat of that gas be felt so that because these galaxies would have also, like planets and all that, how would that be felt within the galaxies as well? How would you feel it if they were far Earth would be one of those galaxies?
Okay, so I understand the question, and I misexplained something obviously, because the gas is actually there all the time. There is hot gas in those clusters all the time. It's the ways in which it's heated are actually still an open question. It's not understood in detail. But there's all kinds of turbulent motions inside the clusters that you would expect would heat the gas. But it is already hot. So when they come together, there is extra heat, because when the gas slams into each other, you get the shock, the sonic boom I described. And to give you an idea of the numbers, since you asked, maybe before the interaction, the gas is 10 million degrees, let's say. But when the shock happens, at least initially, it's 1 billion degrees. So you get another factor of 100. But the gas is hot.
I think the next gentleman was up the back here, midway up the back.
You mentioned gravity waves earlier. Given that there's a far greater percentage of dark matter in the universe than of baryonic matter, what's the potential for detecting gravity waves emanating from the dark matter? And is there any research going on into that?
That's an excellent question. Yes, there is. To answer that, I need to distinguish between the dark matter I need to distinguish between today in the universe and very early times. Even though there's a lot of dark matter today, let's say 10 or 100 times more, about 10 times more than ordinary matter. Gravitational waves are very weak things, and to make strong gravitational waves, it's almost an oxymoron. There's no such thing as strong gravitational waves. But to make them as strong as you can, you need things moving very quickly, and they need to be large masses, and they need to be non-uniform. Okay? You don't get, if I take a sphere, a perfect sphere, and spin it very fast, I will not get any gravitational waves, even if it's fast and it's very massive. It needs to have blobs floating. Okay? Now, by and large, the dark matter distribution through the universe is fairly smooth, and it's not. I mean, there are blobs, but for the purpose from the point of view of gravity waves, it is too smooth and moving too slowly to make a strong enough signal. However, right back at the early universe, shortly after the Big Bang, it is believed that gravitational waves may have been produced in large numbers. And it is believed, in fact, that there's a similar map to this one that you can make for gravitational waves if one day we get to the point where our sensitivity is sufficient to measure it. Okay? Now, in that case, the dark matter will influence, it may not be the only thing that generates the waves, but it will certainly influence the way in which they're generated and the kind of patterns that you get on that pattern. But your hope has to be very early universe, when things were smaller, things were moving faster, and the matter was denser and more complex.
Okay, I know there are people who have got some further pressing questions. I'm sure Andrew will be happy to stay around for a little longer if you want to come down and speak to him directly. I would like to bring the lecture to a close and conclude our 2007 bi-lecture program on breakthroughs. I just remind you about this one. I think something very heavy is moving across the kitchen there. Distortions in the fabric of space-time itself, but please come back and join us for this lecture in today, August the 15th. So I'd like to thank you all for coming and supporting our July lecture program. We appreciate your interest very much. If you'd like to get emails on activities associated with the School of Physics, please sign up on the sheets that are out on the table at the lower door here, and we will welcome you back for the 2008 program in July next year. Thank you again for coming.